Good afternoon. Thank you for participating in these sessions. My name is Xingzhong. Some introductions. I joined Uber 3 years ago. For the recent 1 years, marketplace. So in the recent 1 years, we are trying to pilot Flink in our real-time decision-making systems. So it turns out the progress is pretty good, and we have some good experiences, prototyping, and even in productions. So I would like to say, taking this opportunity to share with our progress. First slide is just some Uber introduction. I hope everybody know what is Ubers. Our mission is to bring transportation for everyone, everywhere. It's a great vision, so I'm glad my work have a good positive impact on here. So today I'm trying to introduce 4 things. First, I will just make some introduction on marketplace. Marketplace is an organization inside of the Ubers. It tackles some of the hardest problems, real-time problems inside of the Ubers. And the problem space is very interesting. So that's our foundation of all the related works. And then I'm trying to introduce 2 specific things that I think the Flink really helped the marketplace. The first one is called geotemporal event aggregations. The other is called online model updates. And the last but not least, I want to introduce, it's most like a conclusions. So it's the lesson we learned towards from the analytics to applications. So we call it the Flink streaming applications. So let's just getting started. I just take a screenshot from the Uber Marketplace website. The marketplace tackle all kind of business related logics. We not just do dispatch, we do intelligent dispatch. We not just do rider pricing, driver pricing, we actually do dynamic pricing or surge pricings. We also do a lot of forecasting, monitor the market. As you can tell, the marketplace, this organization inside of Ubers, we call it a central brain of Uber, because everything after you click some button in the apps, there's a million things actually happen in the backend. 2 things I'm trying to emphasize today. One is what we call the dynamics logistic network, which is you can consider as an inside of the Uber's marketplace. The other part of the Uber marketplace is all about the decision engines. I'll talk later. First, let me define what is a marketplace dynamic. This is some kind of a concept, we just made it up. Essentially, it's just some kind of understanding or interpretation of the current market. So as you can imagine, Uber definitely interests about the past and current and future supply and demand. And we also care about the current trips, current traffic. There's basically a lot of things that we are interested in the current markets. And the decision engine is something that once we get those dynamics, we're not just for fun or for monitor purpose. We're actually trying to using those dynamics to make some decisions. As you can imagine, as a marketplace, we do dispatch, we do pricing, we do positioning, and we also do promotions. One example is when we do make dispatch decisions, that actually means we pair one supply and one demand together and eventually form a trips. So you can understand the entire relationship of the marketplace is somehow like a feedback loops. So at the bottom is our physical world. We are observing this, our organization are observing this physical world through either active or passive to get those events from marketplace. Once we get the marketplace event, we need to figure out some ways to processing that in order to get something what we call the marketplace dynamics. Once we get dynamics, we apply these dynamics along with our machine learning models, statistical models to make some final decisions. And those decisions actually apply to the physical world again. And then we're observing, see if this decision actually makes sense or not. So that the whole idea of this marketplace is very interesting. We are act and we are observing. The first part I want to introduce today is how do we get those marketplace dynamics from the marketplace events? Events processing is definitely something we well understand in computer science. I think every company working on event processing. But there's something unique in Uber's marketplace. We found out that most of companies either just do real time or they just focus on real world. And in Uber's situation, it's pretty unique. For marketplace, we have to handle both. All the events coming through our Uber marketplace, we have to address both real-time and real-world requirements. Let's break it to the first challenges we get. This is what we call the real-time challenges. As you understand, we're trying to get insight from this event as soon as possible. So essentially, this is a time-sensitive systems. But by natures, those events are actually coming from mobile devices. The mobile device, once it comes into Uber, it naturally have out of orders, delay, and long tails. So we have these kind of challenges. How do we somehow make sure we get data kind of complete, or also make sure we can deliver those data as soon as possible? So conceptually, what you really want to get is some kind of this bar graph. You want to get some kind of this time series. Each of the bar is some kind of aggregation result in event time buckets, and we want this as a time series so we can see the trend based on the time. Two things are very important here. For this kind of graph, we really want the data delivered to the user delivered to marketplace as soon as possible. In the meanwhile, we also want it as accurate as possible, because anything delayed in terms of materialize this data will definitely incur a cost for marketplace. And anything if your analytic data is not accurate enough, it will also degrade our marketplace performance. The next challenge we get is what we call the real-world challenges. Uber's marketplace ingests millions of these events. Each of these events actually happening in some geophysical world. So location are already associated with those events. Once you have a geolocation, then things getting a little bit complicated because it's no longer independent, those events. So you're trying to explore their geo relationship. So this is what we call the locality sensitives. And in details, we have some kind of example in here. You can understand each event coming into our system, it's just not only influence its current locations. It's actually influence all his neighborhood. Think about some traffic congestions happening in 2nd Street. Then that means 1st Street and 3rd Street also have some problems. So those kind of relationship are what we are trying to get in. And so the question is basically, how do we aggregate geo-related events in real time? And the initial solution we're trying to, and we are still, some of the applications still using, is OLAP-based systems. The solution is very straightforward. I just write a very simple diagram in here. And I guess most of the company are still using OLAP. The way to understand is that we have a bunch of the events coming as forming as event streams. Once it just keep going. The first block we draw in here is a simplified OLAP system. It can be very complicated, but essentially it's just do one thing. He basically shard your events by event time bucket and by geolocation ID. Then for each of the key, you do aggregation, probably with some database. And once you have this database, it's just ready for your queries. Then the other part of the world will come in as either a service or data analyst. They can query your OLAP system to get a most recent marketplace snapshot. Once they get this information, they can apply some functions. Since this kind of information is geo-related, so normally you have to grab the entire cities because they are all related. So that's typical what we do before. And then we are operating this for a very long time, and we figure out a couple of issues that are really annoying to us. The first one is in the step 2. Particularly this query things. This query things actually is a little bit annoying is because in order to constantly monitor the marketplace, that basically means we need a scheduler. Maybe once a minute you have to call the OLAP to get a snapshot. So essentially, we are bringing external dependency into our systems. Two things will make it bad. One is in terms of reliabilities, this is not good because you have external dependencies. You will be surprised how difficult to write a very stable distributed schedulers in the productions. And if it's encounter any failures, that means the entire city are losing an update. That's what we're trying to avoid. Second thing, because of the scheduler, is forced our pipeline to pull models. As you can imagine, any events happening in this real world, we want to get this information as soon as possible. But because of the scheduler, we have to wait until the schedule triggered. If you configure your schedule once a minute, that means potentially you will lose 1 minute, which is a big thing for Ubers. The second thing really didn't work so very well is this batch snapshot concept. This is also very straightforward. Once you get this entire city's data, because it's a query, you get the entire city data after as a response. Then you have to apply some kind of function on top of that. Initially, it might be works very well, but then after a while, your granularity get improved, which means you have more key and more keys in your snapshot. And your compute function can get very complicated. You can apply a lot of modeling stuff on top of that. Then they start to be a form of computation bottleneck in our data pipelines. And this make us very hard to scale. So then we step back to thinking, how do we fixing this? How do we do this? And then we start to, then Flink start to into in our radars. And we start to adopt those event-driven solutions. The way to work on this is very straightforward. The essential idea is we just break this computational bottleneck to map-reduced kind of styles. The first step is just map. In here, we're just using flat map. The second step is reduce. The tricky part in here is you're just thinking you are event. For example, you probably that red dot. So you understand two things. One is you are not alone in our entire systems. The second thing is you will make sure your impact will be passed on to different locations. The easiest way to make it work is just duplicate yourself at different locations, still honor your event types. So that's actually how we do in productions. We basically duplicate every event coming to our system as long as it's geo-related to different locations, basically broadcast to all the geolocation is related. Essentially, in Flink, we are just using these flat map functions. It converts a geo-related event to a geo-independent event stream. Once you get independence, then things are very easy. If you just want to do aggregation, you just create another Windows, event time Windows, and maybe do some counting, maybe do some other reduce functions. The trick definitely is in the flat map part. So what is the benefit by adopting those event-based design and as well as using Flink? First of all, we already got rid of this periodic query concept. Actually, by using these kind of designs, our entire pipeline is a query-free systems. The reason is Flink provides these flexible windows and trigger strategies. So before, we have to wait for some scheduler to trigger some computations. Now the computation is triggered by events only. This is a very stable designs. As long as you have events, the computation will always be triggered. The second good part is the latency in pipelines. By using this kind of event-driven designs, we are basically convert our computation model to push models, and we also pretty confident about once the information getting materialized, we can track it as a watermark. So basically, once your aggregation window start to materialize, you can immediately push to consumer as soon as possible. That's definitely something we really like it. Second thing is by using this map reuse kind of concept, essentially we're just doing like a space-time trade-off. We can avoid a single point of failure and the computational bottleneck in the entire pipelines. So the computation actually baked into the streaming topologies. By using that, it's definitely a better in terms of isolation and scalability part. It's actually a win-win situations. If you somehow have a more complicated computation, have more geo-granularities, you just throw more machine into your clusters. And the entire thing seems too good to be true. So when we start to initialize, design these things and do some discussion, we indeed have concerns. The first one is by using event-driven this kind of design to replace the OLAP system. So essentially, you are doing excessive fan-out compared to a pretty much shuffle-free OLAP systems. That's a valid concern because in production, as you probably remember, we ingest a million levels events coming to our system. And normally in production, we are found out 1,000 times because each event just have that kind of physical relationships. Then that means a billion level throughput in our system. That seems pretty big numbers. We definitely have concerns. The second concern is by using this Flink job, we pretty much bake our computational logic into the specific customized jobs. But before, the OLAP is more like a generic systems. Anybody can query it. You can write a customized query and to query against a single OLAP system. That's another concern. Is this considered a good pattern or not? It turned out we did some benchmark for sure, and also we did some analysis. It turned out the Flink is right answers, at least from performance point of views. We indeed duplicate 1,000 times, but we figure out the Flink's performance actually out of our expectations. It definitely can hold its value. The reason, I think there's a lot of reason to explain why the Flink have a better performance in these situations. But I just found two things are very important here. One is the Flink is using virtual key instead of physical keys. So but what that means is the key is not the reason to determine the physical data locations. So even you create millions of keys in your runtime or production, it doesn't necessarily mean you need to shuffle around a million times, and which incur a lot of network I/Os. The second thing is we found maybe useful is because before we did some kind of test in other stream platform, we found the memory issues because you pretty much duplicate 1,000 times things. And the Flink have their own memory management, so it seems they can taking care of this memory shock once we do the flat map. The second, in terms of the specific and topology, that kind of discussion, I think that's still a valid discussion. The takeaway from our point of view is like once you actually read a data stream API and data flow languages, you start to realize the API itself is very intuitive and simple. So we have a feeling that if you can read and write SQLs, you probably can read and write data flow APIs as long as you have a proper infra support. The second take is that I think it's still good if you just for analytic purpose, OLAP is still a good solution. But if you can justify your application business values and you have a real-time requirement, just like marketplace requirements, then you probably really need to customize a job for your application. It's better in terms of isolation and consistency. So that's my view on that. The second part I want to introduce today is, we already covered the first part. The second part is, once we have this marketplace dynamics, which means aggregating values, how do we coming up with decisions? Specifically for this talk, I just trying to cover the online machine learning model updates. The way to consider is a marketplace really is what we call a model shop. We hire a bunch of engineers, data scientists, even professors. They all have their views to describe the world one way or another. And what we are doing is basically first train the models, make sure the parameters are accurate enough. Then we do decision making by acting on those models. So I think this is not a good time to talk about machine learning stuff. So I just have my basic math in here. When we say we are trying to fit in a model to real world, it actually means doing some kind of optimization problems. And from very high level point of views, it actually have two basic input. One is what we call the word dynamic stream. This is just what I just introduced, the marketplace dynamics through the event types. And the other part of the model is just model parameters. The whole idea is you're trying to optimize the theta. You find the best theta, and along with the model to describe these physical word dynamic streams. And two things are really in our radars, as actually is our challenges. Once you feed on models and you deploy to the productions, the most difficult part is how do you handle the real-time signals. Before we probably, in this picture, for historical pattern, I think this is a well-known issue. When people talk about machine learning, they mostly talk about offline things. The idea is very straightforward. You get this data warehouse, which contain all kinds of data. Then you can write a job. Depends on your application, it's maybe just a Hive query, or maybe it's very complicated. You need a TensorFlow and Spark to load your data. But essentially, it's just filter out the data and do some estimation, find the best parameter, and saving somewhere for future usage. This is work very well, but the problem is, if this is a weekly job, then something may happen in the middle of the weeks. Then they make your model stale or degraded. And we have to figure out a way to handle this. One way to do that is, if anything just happened, you just re-trigger your models. But if just real-time signals are just constantly coming to your system, then you'd better just find better ways to do that. And the real challenge for real-time modeling, obviously there's a lot of challenges. We found two things are very hard. One is data sparsities. If you just rely on your real-time signals, then your model will never converge probably, especially if your parameters dimensions pretty high. So we really need to figure out a way to how do we bootstrap the real-time model with consider the historical data. The other part of the problem is the computational pattern is really different compared to the most what we already familiar with stream processing. It actually need to do some kind of iterations, and sometimes we have to wait for their convergence, and sometimes if your model is so super complicated, it may never converge. So it seems like these two things are actually our blocker to make it on the productions. And in Uber's, the way we partially solve these problems is just using these classical online, offline hybrid solutions. There's a three-step basically from principle levels. The first step is you just need to make sure your model support incremental trainings. If your model just cannot take additional incremental data, then it may not work in our situations. I believe luckily most of them, you can always convert your model to support it, at least from my understandings. There's another two steps. The first step is our old step, which is using offline periodical job, weekly job to find the parameter estimation. Then we deploy another stateful Flink job to do the parameter calibrations in productions. This is what we just mentioned, the offline job. The only difference here is before the offline job is gonna generate a theta, which is considered as a best theta. But now we relax this kind of assumptions. Now the theta is our initial value. It's just basically some good value based on the current data. It will change. And we already know this is a time invariant. And in online part, we're just using this Flink job to do a stateful updatings. It's a lot of details, so I don't want to talk this too much. But essential idea is that the offline job gonna produce some things, and in the real-time job, gonna using RPC to load that thetas in the bootstrap. Then we're gonna iterate on this state as a state because it's stateful. We're gonna iterate on this state, find a gradient, wait for convergence, or wait for some other threshold trigger. And the good practice is always make sure to reduce your parameter dimensions. This only work if your dimension is kind of small. If you have a 100 vector like a dimension parameters, that gradient method will probably never converge. And essentially, that's our whole pictures. I just don't want to iterate again. The good part is here. The events coming through Kafka will go through two paths. Once go to the real-time signal, once will accumulate in the data warehouse. And the offline part will periodically train the models based on the historical data. The historical data is also incremented, just a little bit delays. In the real-time job, we always first try to fetch a good initial value for the models, and then we just keep iterating on that. The good part of this is our real-time Flink job, because our requirements are pretty critical. So sometimes the real-time job may down, or it just didn't work. Then we can still, because it's load the parameter in the bootstrap. So ideally, we can still using some styled parameters. It won't actually block our optimizations. So that's the use case I just introduced. I want to give some thoughts in terms of this stream Flink usage in marketplace. So essentially, I want to start from this two-story recap. If you understand my first part of the story, it's really just like how do we getting events from dynamics? Essentially, we're doing analytic works. The way to solving this is we're writing our Flink jobs. We transform those raw events to an aggregation result over event times. The second story we get is once we get those dynamics, how do we incorporate real-time signals to calibrate those decision-making model? Once we calibrate those decisions, then we can, based on that model, once we calibrate the decision engine parameters, we can, based on that model, to make decisions. So essentially, we write two Flink jobs to make it as a pipeline. So then the natural question is, why not we just write a unified, a single, gigantic job that do all of the work together? That's actually the things I'm currently working in progress. It's not ready yet. The previous part is already in production. This is still work in progress. If I get some progress, I will try to report it next times. But the essential idea is that before, people writing real-time Flink job, people writing stream job mostly for analytic purpose. But now by using this, we can use this unified job to really do end-to-end solutions. Then it seems a very good vision. We have a single per each of the decision-making application. We just write that single Flink applications to observe the marketplace events, do that in stateful, act on that, update the models, and just making decisions. We can do this on dispatch. We can do this on pricing. And by using that, we can eliminate a lot of engineer overhead. Think about before we are using a microservice. Then you have to do a lot of services, caching validations, database layers. It's basically a lot of work in there. Another good part of the things is that because this is so simplified, it's actually very easy to do simulation and backtesting. As you can understand, we are just basically do optimization models in real time. So we really need to try different models in a simulation world to better improve the systems. So there's a lot of good opportunity to working on this, but still work in progress. But I do have some lesson learned. We are using Flink for 1 year, I guess. There's some good lesson we learned, obviously. The first and most importantly is strong infra level support. Luckily in Uber's, if you just listen in the previous session, one of the Uber infra is giving a talk about Flink as a service. So without those kind of support, it's really very hard for a product team to working on those things. And if you're familiar with Uber's, we also have a machine learning as a service, and machine learning as a service. So those offline jobs can also be easily triggered by their support. Without those, we cannot do those kind of stuff. The rest of them are mostly about real-time machine learning. We have tried real-time machine learning a little bit, but the general conclusion is pretty hard. I guess most people, if you really try that, you figure out this is a pretty hard problem. And there's a lot of reason to explain why it's hard. One of the good reasons I found is not about the performance. It's like you can using more performant TensorFlow to find a gradient or different numerical optimization method. It's most about the data pre-processing. Align the data in event time because it's a multiple data stream. You have to join them together, align them together, make it available for machine learning usage. It's actually very hard problems, and it requires a lot of iteration and tunings. That's the most difficult part. My thinking is that if you already have a good data, you just have okay models, then you probably already finished the 80% of your work. But if you have a very good models, but you don't have a good alignment in terms of data, you probably can't do anything. That's the lesson we learned. And if you really want to do machine learning in real time, there's two things I think is more important. Just try to bootstrap your model in offline mode. Don't try using a streaming job to solving all your problems. It's just too naive, probably. It's just difficult. And if you really want to do machine learning, like gradient, those kind of methods in the real time, another thing is you have to make sure is you try to reduce your parameter as much as possible. In production, well, basically, we have a high dimensional. We probably have a high dimensional parameters. We basically separate to two parts. One is more sensitive for historical data. One is more sensitive to real-time data. By using this way, we can reduce the dimension and make the convergence faster. That's pretty much everything I have. Happy to take questions.
Any questions for the user, for the speaker? Sorry.
For your online ML or machine learning, are you using any other tools along with the Flink, or it's just a standard library that Flink provides?
Yeah, we use some open source optimization solver. We're not using TensorFlow yet, but we are trying to using that. Right now, our model is not that, because it's a pure real-time things. We don't want to introduce a heavy dependency in that part. We are mostly focused on the data pipeline part. So right now, the optimization solver is something called IPOps. It's open source solvers. Sometimes we just basically write Java code to do that.
Okay, and when you do the OLAP as well as the online training, if there is an anomaly into your data, because it's like, very sensitive data and it can change your model, how do you detect it, or how do you prevent that from happening into your system?
So you're asking,
basically, when you have a bad data because of some intermittent ecosystem, that may potentially impact it, right?
Yes. That's why we have these offline jobs, and we're using the parameters only a state. So if this is something we are still trying to improve. If our model accept some very bad data, it basically crash the entire model. Then we just restart it, start from the old beginning stealth multiplier, and start to train them again.
Thank you.
I have a question about the direction you're going. Explain that you combining metrics aggregation with decision making as a one app. In that case, basically you need to have analytics need anyway, so you have to have a analytics aggregation in different Flink job, and then so maybe data, there's discrepancy between the decision making app, aggregate the view of the data versus analytics view, like those kind of concern. How do you address those?
Not quite understand.
Yeah, basically you're basically combining aggregate metrics aggregation with the decision making, and then in that case, those usually when you separate them out, the aggregation can be used by multiple applications, right. And then they see the same view of data. But in this case, you might see the different view of data or like those.
Yes. That's definitely our concerns. Because the intermediate result have other cool usage. Yeah. So that's why we write to Kafka another copies in the runtime. So basically the topology will have in the middle of the topology there's a sink to sync to the Kafka. You can have another hot OLAP system to ingest in that for the analytic purpose. This is pretty much just for the critical real-time purpose.
Basically, there is another aggregation path, and then this is application do aggregation again, but plus with the.
Yeah, I mean aggregation, because aggregation is mostly like a definition. It's like once we define what is the supply, what is demand, we have to agree on that. So probably that's only one job. But after you have those analytics, then how do you interpret that may depend on different applications. Then we pretty much just dump the analytic to the Kafka. And there's another system just they don't do aggregation, they just pick it up and for how purpose, how to use it for purpose.
Any more questions? So let's thank the speaker once again.